So welcome back. In this video, we're going to move on from our topic of the last time where we talked about the analysis of doubly reinforced rectangular sections. And we're going to look more at the design. And so the design approach is a little bit trickier, but I'm going to kind of walk you through the process and some considerations. And we're going to compare this to the methodology that we used with the singly reinforced approaches a couple of videos ago. So my intent is to kind of walk us through this process. So without further ado, here we go. All right, so if you recall from last time, we talked about the effects of compression reinforcement on the strains of a cross-section subjected to the same flexural moments, okay? By adding this reinforcing, it can have a fairly pronounced effect on the overall behavior of it, okay? In fact, we talked about some of the reasons in our last video of what compression reinforcement can do. It can help with long-term deformations. It can actually provide you extra capacity by forcing the tensile steel to yield. And those are all beneficial things for us to be looking at. So what I've done is I've kind of come through and I've drawn the two scenarios that we have. First one I'm going to draw is an SRR beam. And the second one is the DRR, the doubly reinforced. So you can see here I have tensile steel AS, and then for the same beam with the same tensile steel, I've come in and I've added a couple of extra amounts of AS prime at a location of D prime from the top. Now everything else is the same as we've done before. It's B wide, D depth, and this becomes the strain diagram that we have, all right? And so what I've tried to illustrate here is that if we look at what happens, okay, epsilon CU is still listed as 0.003. That's our particular value. And so the strain diagram from case 1, our SRR case, would be represented by this dashed line that's here. All right, and so the effect of what happens to the strain diagram, when I add AS prime, you'll notice that, the strain that was at this level went all the way out to the dashed line, but when I add steel into it, the strain is going to decrease. All right, so if you think about this point at the top of the beam as being kind of a pivot point, the solid line becomes the location of the strain diagram when I put that extra steel in, because again, we're sticking with the assumption that plane sections remain plane, that it is a linear strain diagram that exists between these, but there's a little bit of a difference between here and here now. Okay, and that's what we're looking at, because this is where it was before, and then this is where it ended up after. That strain at that location where the compressive steel has been added is decreased. Now, by decreasing that, all I do is I come up and I make a new line. That, so before we were here, like this, and then I keep that point on ECU, and I basically put this over through the new strain value at that location, and you can see that the strain diagram changes. And so what happens is now the strain diagram on the tensile steel, that there's some change in strain, some delta strain there, that now this thing gets longer, meaning you're putting more tension strain into the steel, which means more tension stress, which means more tensile force. Okay, we're going to end up being more likely to yield the steel if it hasn't already by adding that compressive steel. So this interaction of the strain diagram is a very important idea to try to kind of wrap your head around. And then if you can understand the pictures and how they're constructed, then you can play all sorts of what if games on this. What happens if I change the depth and keep everything else the same? Well, obviously, or if I move the steel further down in the cross section, those kind of games can all be played off of this picture. So that's why I present this, as a methodology for kind of understanding the overall behavior of these two. So that was kind of our side-by-side comparison. Now, if you look at the picture, some things that you want to notice is that for both of those cases in the picture, the strain in the concrete was the same value. It's 0.003. That remained unchanged. Okay, the second thing to notice is that the strain in concrete at the location of epsilon S prime, that's this guy, for number 1, does not vary a whole lot from what it was for number 2. It gets a little smaller, but not much. Okay, it's not a whole lot of difference. Okay, so basically we can say that the epsilon S prime for number 1 is about the same as epsilon S prime for number 2. Okay, the strain at that location. Now remember that we don't have any steel in case number 1 exactly, but the strains at those levels are basically the same value. Okay, but what happens is, and this is where you get the most bang for your buck with the compressive steel, is that the strain in the tensile steel is significantly increased for case 2 when you compare it to the case 1 that had no compressive steel. Okay, this can be used to help ensure that yielding occurs and can significantly impact the selection of phi. Because remember, if I don't get epsilon T greater than 0.005, that's the only way that phi is equal to 0.9. If I'm less than this, my phi starts drastically reducing. So this isn't forcing us to yield the steel, which is ensuring that we get a ductile failure before we get crushing of the concrete. So it's an important concept, and it's illustrated by the picture of that strain diagram. So that's a huge point to pay attention to. All right, now in the last video we talked about some reasons to add compression steel, and I wanted to kind of provide some more information and some more background on this, because this will kind of help us with some of our design thoughts as we go through. So reasons to add compression steel, okay, that the first one, and probably one of the biggest one, is that we can reduce the sustained load, okay, or what we call the long-term deformations, you know. And so from a series of tests that were conducted in the 1950s, okay, this picture shows for a simply supported beam the effects of our deflections by adding compressive steel at what we call a rho prime of 0, meaning no compressive steel, all the way up to a rho prime, the compressive steel ratio being the same as the tensile steel ratio. All right, and so if we look at it, you can see that on this axis they're plotting the midspan deflection, delta, for a simply supported uniformly loaded beam, okay, and then we're monitoring the deflections based off of, you know, some time scale here. And so we've got, you know, 120 days, 240 days, all the way out to, it says 2 years, but that would be 240 days, but you get the idea. I guess that should be a 3. That was a typo on that. So 3 years there, okay? And so for a case where I have no compression steel, that top curve is what we were seeing from these tests, okay? And that the deflections were, you know, starting out somewhere around 5 inches and creeping up, you know, to something close to 6, okay? If I go in and I put in equal amounts of tensile steel and compressive steel, you can see that I basically cut that almost in half. Okay, so the initial displacement was 2 inches. It's those long-term effects that, you know, go up, you know, almost 2.5, 3 times as much, are now greatly reduced by putting compressive steel in there. So if you have a deflection-sensitive arrangement of your beam, you know, then adding compressive steel can greatly help you with these long-term deflections. Okay, and so that's something to kind of keep your eye on. Okay, creep is kind of an interesting animal behind the scenes. Okay, the other thing that we can do, and we talked about this back with our SRR beams, is that by adding the compressive steel, I increase the ductility. Okay, basically that moment curvature diagram that we had before, you know, are dramatically increased. Okay, and so for a case where I had a rho prime equal to 0, meaning no compressive steel, I might get a curvature diagram that looks like something like this. So here's, you know, my yield point. You have a cracking point that's not shown on this diagram, then my first yield moment, and then it kind of behaves something kind of like this, and it would end up dying out at about a curvature of, you know, about 4.0 times h as a percent. Okay, but if I come in and I put in the compressive steel on this thing, look at what happens to the curve. It goes well past, almost to double what you were getting before. Okay, so that's a huge advantage. Now, you notice that the moment curvature relationship doesn't really change a lot. I mean, it's still following the same basic path up here, and there's not, I mean, because there's not a lot of difference there. There is a little bit, but not a huge amount. But it's the length of this thing, it's that curvature item that's huge. It's meaning you're getting a whole lot more strain, because remember, curvature for us, you know, for a strain diagram that's linear, curvature is a measure of that angle. Okay, where this is my epsilon top and this is my epsilon bottom, again, for a linear relationship. So what's happened is when I didn't have any steel, it got to about here, and then when I put in the compressive steel, it was able to go a whole lot further and rotate a whole lot more, which is good for ductility. Again, all this has to do with ductility. Okay, all right, the third item is that we can actually change the mode of failure from compression to tension, okay, when I have when we looked at the reinforcement ratios, and this is using our balanced reinforcement ratio that we talked about a couple of videos ago, which is the definition where I fail the concrete at the exact same instant that I fail, or the tensile steel, or not fail, but I yield it. So I hit 0.003, we're plotting strain at the exact same instant that this guy goes to epsilon y. Now again, this is kind of a theoretical point. It may or may not happen for any given beam, but that's kind of our balance. And we know that if my rho that I'm providing is less than the rho that corresponds to this, we're in an under-reinforced state, which is usually ductile. And if we're over that, we're into a compressive state. All right, now what happens is a beam is considered over-reinforced when rho is greater than rho b. Okay, and this usually results in failing the top of the section again, for simply supported positive moments, failing the concrete and crushing. Okay, what happens is, as we saw, is that by adding compression steel, we can increase the strains and the tension reinforcing on this thing. Okay, that was that diagram I showed you on the last page. Okay, and so this is good news for architects, because what they can do by adding compressive steel is they can greatly reduce the dimensions of the beam, okay, while maintaining the moment capacity and still ensuring that the ductility. Okay, now the question becomes, is this good news? Well, maybe, maybe not. Okay, one of the problems that we have is that for cyclic load cases, which are, seismic events or vibrations where loads may reverse, and all of a sudden what's in tension turns into compression cases, okay, the minimum dimensions on B and D are controlled by the limiting reinforcement ratios. So what they've done is they've kind of come in and they've kind of plotted, and if you look at this, the formula in this graph here, I have an MU over my concrete stress over BD squared, okay, or BH squared. This is like basically calculating that R factor from those tables that we're dealing with. Okay, and so what happens when we look at this is that for the set of experiments they were doing, they had a row of 0.0.3 and a row balance of 0.0285. Okay, in the case where I have no compression steel, you can see that it builds up and then it just dies. Okay, as soon as it cracked, it was done. In a reversal case, because there's no steel to arrest that reversal where the compressive side now goes into tension. There's no reinforcing there when the load switches on you. Okay, whereas if I put a rho prime equal to half of rho on there, just that little amount, you can see that the ductility is greatly increased, as well as the moment capacity, okay, will be greatly increased for a given set of dimensions. So that goes up a little bit. And then if I put even more steel into compression, rho prime equal to rho, then I can get a huge increase in the ductility as well as the moment as I start to kind of work on that. So those are some interesting things that can happen with our compressive steel cases. All right, now, because of this sphere of reversal on here, they set a maximum limit on the reinforcement ratio, okay? And this is found in a provision in ACI 318, the 19th edition, 18.6.3.1. Okay, in which they limit the maximum reinforcement ratio for both the tensile steel and the compressive steel to 0.025. Okay, that would be the equivalent of 2.5% of the gross cross section can be steel. Okay, and what that does is that keeps you from, in the case where all of a sudden my signs flip, and I have a whole lot of steel in compression, well then maybe if I don't have as much steel in tension on this thing, that think about it this way, that I put a really big bar here and a little bitty bar there, and this is my AS and my AS prime, and normally we're looking at a minus here and we're looking at a positive and the stress there. If all of a sudden, this was a safe play, I put all this steel in here to force this guy to yield, if all of a sudden this thing flips on here, all of a sudden you have a scenario in which you could end up over reinforcing that side of it and failing the concrete and compression down at the bottom. Okay, and so that's why they limit the amount of steel that you're allowed to do. What this does is this basically forces you for a given moment, it forces you to set your dimensions of your beams, B and D, such that, that you're not overplaying the work of the steel because of these reversals. And that's kind of what's happening. And you'll see a similar provision for this later on when we get into shear analysis, that they don't want you, cranking down architecturally on a beam size to something really, really small and then just loading it up with steel, because now you can get situations where that's not a safe situation to have at all. Okay, all right, so with that kind of hopefully expands a little bit more on the idea of the effect of our compressive reinforcement on here. Okay, so now when we get to the design of DRR beams, okay, the main thought to remember is that simply adding compression steel does not greatly increase the moment capacity of a section. Okay, now what it does again is it increases epsilon s, which if that increases, then epsilon t is also going to go up. And typically, if you were at phi less than 0.9, you have the potential that phi will go up in response. Okay, to a point. Again, this is capped out at 0.9 maximum, but if you were sitting down at a phi of 0.65, the lower bound, all of a sudden putting compressive steel, this guy will drastically increase, and that will increase the moment capacity, the design moment capacity. The nominal moment doesn't move much, but the design capacity does. Okay, and so but more often than not, it's the ductility, increase in epsilon s that we are after, okay, because that helps us with the phi factor on here. All right, so here's our methodology, kind of like what we talked about with the singly reinforced design video, okay? In our sections, we have several unknowns. We have the methodology for us is we're going to look at the unknowns of the width, the depth, the stress block A factor for Whitney, the amount of steel in tension, and the amount of steel in compression. Okay, and now for design, typically we kind of look at, well, how do we want to start? So the approach I like to use is I'm going to select a target value for my tensile reinforcement ratio. Okay, now normally what I do is I set a tensile strain down at the bottom, such that I'll prescribe this value here to be somewhere around 0.004 as my epsilon t strain. Again, we're doing 0.003 up here at the top. Okay, now you look at this and you might say, well, why wouldn't you just go to 0.005 on this? And the answer to that is because at 0.004, even though my phi is less than 0.9 for this guy, we haven't considered the effects of the compression steel. And as we showed in the diagram, if I add steel at this elevation, this diagram is going to lean over and do something like that. And so this strain is going to grow. Okay, so this will get me close to 0.005 without getting, too ridiculously far over it. Okay, so that's the idea that we're going to look at. So what will happen is when I make that assumption, I can kind of design this thing almost like an SRR beam to get the bottom reinforcing, and then I can know that my compressive steel is going to add a little bit to it. So the thought here is that, that by adding AS prime, this will cause that strain to increase. Okay, so that means that we should be okay for a phi of 0.9 for a preliminary round. But again, you must check this thing at the end once you've got everything set. Okay, all right. So the next step then that we're going to look at is we're going to set my epsilon t to 0.004 and determine the location of the neutral axis on the strain diagram. That should be no surprise, right? And so the location of the neutral axis is still located at C. We're at 0.003 here. I artificially set that at 0.004, and then I can use this proportion, the same as what we've been doing all along, to be able to determine out, the finding C based off of D. And you'll notice that this formula, when I do it, that C is equal to 3/7 of D. And this is a formula that the Nielsen textbook that we talked about in the first video, the book that's kind of the backbone of this class, that Nielsen textbook, they use this formula a lot, but they don't exactly tell you why it is that they're doing that. So this 3/7 the depth is a good starting guess for the location of that neutral axis, the C parameter that we have. All right, once we do that, then we can go in and we can start to compute our Whitney block items. Okay, so our C-res, so if you remember, we're looking at a diagram that's going to look something like the following, that you've got a C-res, we're going to have a CS, and then we're going to have a TS here. And again, if you don't remember all of this dimension will be A, okay, and this dimension here is D prime, and then D down to the other one. If you don't remember all this, go back and take a look at the video right before this one, and we'll help refresh your memory in that case. Okay, but from Whitney, just like you've done before, this compressive resultant is 0.85 F prime C B times A. Okay, and then what I've done is, if you recall that A was equal to beta 1C by the Whitney method, that's all I've done is substituted A in for that. Okay, and so when I plug all this in, if we take advantage of our 3/7 D value, I can do 0.85 as 3/7 of beta 1 F prime C B times D will get us our compressive resultant. Okay. Now, for our SRR analysis, you'll recall that we kind of went through and we could estimate some of these, the approximate depth of the Whitney stress block as we did before. And so this is a slightly different variation of the formula that you saw, but if I take my equation for this, I come up with a relationship in which I can show that ASFY over BDFY is equal to 0.36 beta 1 F prime C and BD. So I'm dividing both sides by BD on this thing, because what happens is AS over BD becomes a row value. All right, and then I divide both sides by FY, and so what happens is my BD cancels. So this was that slight variation of the formula that we had before. Okay, but it still works. And so now I've got an expression for rho. And so in this case, when I use this rho, I know everything. I know my concrete strength, I know my steel strength, I know my beta 1, and of course 0.36 is a constant. All right, so you can calculate the rho based off of this assumption of 0.004. Okay, so it becomes very, very easy. All right, so now here's what we do. Okay, we take our beam, okay, and we're going to design the beam first as an SRR beam. Okay, which was our design 1 case when we were analyzing that. Okay, and we'll worry about the compression steel a little bit further down. So you do it just like you did before. We can calculate using that table A5. This was our structural resistance factor tables. Okay, where R was equal to mu over phi BD squared. Okay, and so I can find an R for a given rho, Fy, and F prime C, because those were the 3 parameters that we needed to get into it. Okay, so once I do that, I can pick off my R. Okay, and then once I have R, based off of all of this, I can then come in and compute BD squared as being just M over phi times R. All right, okay. And so that will get me to this. And then to unravel this, all we're doing is we're going to assume a B over D ratio, if you will. Okay, and I think I have this backwards. That should be a D over B ratio. That the width, that the depth to the width ratio is somewhere between 1.5 and 3 is usually the most economical. Again, this is just kind of a rule of thumb on there. Okay, and so from this, if I make an assumption, I like to use 2.0 is pretty common as a value there for that ratio. And if that's the case, then I have D in terms of B, so D is 2 times B. And then I can plug that up into here, and I can actually solve for B and D that will make that happen. So now with that, at this point on step 7, I've now computed the dimensions of the cross section. Okay, so then you can come in and you can compute the tensile steel requirements. And so AS required is going to be rho times BD. That's just working this thing in reverse, and we can select our bar sizes. Okay, now make sure that once you've done this, when you selected your bar sizes, that you need to check the width of the section, right? We had that BW minimum. That was a function. Remember, if we have our stirrup that has some dimension here, and I put a couple of bars and some spacings, that it was, the cover plus the stirrup thickness, plus that gap distance, plus the diameter of the bar, plus the spacing, diameter of the bar, spacing, diameter, and so forth and so on. That was the dimension that we were looking at here to make sure that all of the stuff that I've chosen will fit into this. And if we can get it all in one layer, that's great. But if we need to go to 2, then we need to know that as well. Okay. Now, what happens with this methodology is that this design procedure will result in a beam section with a relatively large amount of tensile reinforcing, all right? Because you're not taking advantage of the compressive steel at all right? But it is a good start for a design. Okay, so what we're going to do then, typically, again as a design approach, is I'm just going to assume, and this comes out of those charts that we showed in which they took the compressive reinforcement ratio and set it to half of the tensile ratio. Okay, and so what we're going to do is we're going to select AS prime such that it's greater than 0.5 AS. Okay, and so this is based on older ACI codes, okay, and the seismic provisions that they had that requirement. And again, this has to do with that reversal. You want to make sure you have enough steel on the reverse side when things go from tension to compression, that I have enough steel that I don't get a sudden failure kind of because of an over-reinforced situation. Okay, and now, even though it's not common in the current ACI code, it is a good rule of thumb and gives me a tremendously good first guess for AS prime. Okay, so that's one of the reasons I still kind of incorporate that into the methodology. Okay, so then we can go in and we can look at doing our modified Whitney block as we did before. Okay, and if you remember, this was the B case. Okay, and here we had C-res. Okay, and if you remember that what we did is we found the moment capacity of the compressive reinforcement for the amount that was equal to the tensile reinforcement amount as the first case, and then this becomes the additional moment. And so from this starts to look a whole lot like a singly reinforced case. But you'll notice that this is our T sub B. I think we called it T2 in the last video as we look at that. But that's the difference. So here's the steel, what the steel is doing, and here's what the compressive steel is doing. Now notice I haven't assumed anything in terms of the stresses. I'm just saying that the stress in this and the stress in this. Now hopefully this is Fy and may or may not be Fy, we don't know. But when I do that, when I do my sum of forces in the X equation like we did last time, I can solve for A. by simply taking this value and dividing by 0.85 f prime cb, because that was this guy, 0.85 f prime cb. That will get me there. Okay, once we have that little a, I can then compute c. Okay, and then we can move in and compute the strains using the proportions just like we did before, epsilon s prime, and epsilon t. And basically that will verify our assumptions of about fs and fy. Okay, this part is all exactly the same as the analysis that we did before. Okay, but once we check this with verify, we've got to have fs equal to fy, and then for phi, we want to make sure to check that epsilon t parameter. Okay, so finally, we need to make sure about epsilon s prime. Did it yield or did it not? Okay, if it didn't yield, okay, we go back to step 10 and we have to recompute a. So the initial assumption we make is often that fs and fs prime have yielded. Okay, and then from then on, it's pretty much the same game as what we did before. We can verify that our moment is sufficient, and then, as we did in the moment diagram. Okay, now, the thing to recognize is up here, we may fail one or many of these, and we may have to iterate a couple of times. But that's the general procedure for the way that I like to start to guess things, and it's generally pretty good and pretty accurate for us. Okay, so finally, kind of again the worksheet that we kind of work through just to kind of again illustrate the thought process on these is that for doubly reinforced considerations, our first example would be looking at some sort of integrated slab beam for a high-rise office building. Now, I'm going to preface this by saying we're going to completely neglect the shaded regions. I know those of you that are familiar with concrete design are going, well, that's a T-beam, and we need to consider effective flange width. All I'm doing is looking at making it so that the stem does all of the work on this kind of thing. And that's fine because even if the flange becomes active, all that does is it increases the strain down on the steel here. So this is kind of a conservative guesstimate. It's not very efficient. It's definitely not economical, but that's the way that we're going to set this up. So what I've done is I've set up that the slab is 6 inches thick. Not that that matters. We have 12 inches on the ears of this thing, and then I have a B width and a depth overall of 20 inches. Now maybe this is coming out of those minimum tables or an architectural requirement. I don't know. And then for now we'll assume that there's a number 3 stirrup that's being assigned right there. Okay. So factors that were given in this, the max aggregate size is let's see if I can read that, 3/4 of an inch. I know it's a little small even on my page. So it's a 3/4 of an inch max aggregate size. Okay, again, what this does, this gets me to my spacing requirements. It's one of the factors for spacing. Okay, and so we'll use that to check our minimum width to make sure that we can get our reinforcement once we get to that point, that we can get it all fit into the section. And then basically F prime C is 4,000 and PSI, and FY is 60 KSI. Okay, and so like I said, the architect has set a maximum depth of 20 inches for whatever reason, instead of using the ACI minimums. And then what we're going to look at is what's the negative factored moment on this beam of minus 229 kip feet of this. Okay, so what we're doing, as I said, it's one of the assumptions that we're going to make right off the bat is we're going to neglect the contribution of the slab and the flexural capacity. All steel must be placed within the beam region, though multiple layers may be used. So it's basically, this is a DRR problem, just like I said. Okay, what we want to find is we want to find the beam dimensions and the tensile and compressive steel requirements. Okay, the section must be doubly reinforced DRR due to ductility concerns. Okay, so all we're going to do is we're going to walk through the process that I outlined before. We're going to choose a target row for a tensile reinforcement. And when I do that, we're going to estimate our strain. And remember, all this is, we're just estimating this guy at 0.004 as our first guess, and then computing the corresponding row off of that. Okay, so then we're going to look at some of the assumptions. We're going to take some assumptions about epsilon T and phi to go in, and then we'll be able to go in, based off of these assumptions, tensile steel does or does not yield. So figuring out, well, okay, does our steel yield if it's at 0.004? Well, most definitely it does. Okay, so then what's our phi? 0.9 as a guess. Okay, and then if that's the case, what's our corresponding stress in the tensile steel? And then guessing about the compression side of things, what's it doing as well. So again, once you make this assumption, you should be able to draw the strain diagram and conclude whether one is yielding or not. Okay, like I said, the tensile steel most definitely is, but the compressive steel may or may not be. Okay, and then we're going to take a guess on the B over D ratio. So these are all things, again, that I kind of gave you some rules for how to guess those on the first pass. So again, I typically choose that to be 2.0 as I start to look. Okay, So then you go in, and so we're going to find B and D for an equivalent SRR section. So all you're going to do is go to the R tables, compute the R, and then this will get me B, and this will get me D, so forth and so on. And then once we have that, okay, all we're going to do is we're going to take a first guess for the area of the tensile steel, all right? So all we were doing was taking AS and setting that equal to rho times BD, and the rho was what we were guessing way up here at the very, very beginning. So it's not too bad. Okay, once we've got that part set and we've got our dimensions figured out, this is now just a DRR analysis problem. So we're going to compute the A, the depth of the block. Okay, we're going to check our guesses for AS and basically recompute A until convergence. So what happens is I get an A, so I've got an AS that gives me a little A, okay, and then I choose a set of bars that's going to change my A, which then is going to change my AS, and so we're going to iterate through a couple of times, and eventually we'll come to a value that's a pretty good estimate of what's happening here. Okay, and then finally, all that's left is to check the neutral axis for the cross section, and then compute the strains that verify our assumptions. Because again, you've got to verify, that FS is that still equal to FY? Is FS prime less than or equal to FY for the derivation, and then adjust accordingly. Okay, and then of course epsilon T, that gets me to my phi. What's my phi value? Okay, and so that's where the calculation that we need, and then this is where you actually verify the assumptions. Okay, and then we go in and we can add our compression steel using our 50% rule of thumb. Okay, and then basically once you add AS prime, then recompute A, and you go back around through the process just like we've outlined before. Okay, and then finally, once you've got all the steel figured out, now you can finish up your strains. These are the final strains. The ones on the previous page were just kind of guesses. And then again, verify your assumptions. We want to make sure that epsilon T goes greater than 0.005 to ensure that our assumption of this was true. Okay, and again, you don't want to be like right on that number. Give yourself a little bit of room to work. 5 or 10% is probably sufficient as we start to go. So, and then finally, check your flexural capacity of your design. Is it greater than MU? And if it is, you're done. You got it. So anyway, that's the approach for kind of a DRR design. It's a little bit of kind of guess and check and making some assumptions. But if you don't use some of the tricks that I showed you in this video, sometimes you can get stuck in kind of an iterative loop, for a couple of extra cycles before things start to converge. So I'll leave this as kind of an exercise for you guys to kind of work through. And as always, leave us some comments at the bottom of the video. Let us know what worked or what didn't. It didn't make sense, or is there something else that you would like to see on this topic? And we can always add more videos into the sequence if there's enough demand for it. So as always, toss us a like on the video, and please be sure to subscribe to the channel. We'll keep the content flowing at that point. So thank you for your time. Have a great afternoon, and we will see you next time. Happy engineering.